Hello all, welcome back to my YouTube channel all about VLSI. In this video, we are going to discuss about frequency division by odd numbers with 50% duty cycle. Now, before going to discuss about 50% duty cycle, let us try to understand why do we need 50% duty cycle. So basically a 50% duty cycle means high time is equal to low time. The signal duration when it is high, which is equal to the signal duration when it is low. Okay, and this ensures equal time for setup and hold operations in sequential circuits. If you have a 50% duty cycle, this is going to ensure that your setup time and hold time operations is equal for sequential circuits, and flip-flops and latches get balanced timing margins when both rising and falling edges are evenly spaced. So that's why we need 50% duty cycle. And one more thing is simpler clock distribution. So in large chips like SoCs, FPGAs, ASICs, your clock trees are designed assuming 50% duty cycle. So it is going to basically ensure that balanced rise to rise and fall to fall timings, simplifying the timing closure, as well as maximum performance utilization. So with 50% duty cycle, the timing between rising and falling edges is equal. And some designs like DDR use both edges of the clock, and in non 50% duty cycle would means one edge has less margin, reducing the effective speed. So these are the reasons why we are going to prefer the 50% duty cycle majorly. Now, how to design this 50% duty cycle, frequency by 3, frequency by 5, frequency by 7 with 50% duty cycle? First of all, in our previous sessions, we have already seen what do you mean by duty cycle, how to calculate the duty cycle, and what is the duty cycle, and how to design frequency by 3 clock frequency, and what is the counter which we are going to take. Okay, for frequency division by 3 we are going to consider a mod 3 counter, and if we consider a up counter we are going to get a 33.33% duty cycle, and if we are going to consider a mod 3 down counter then we are going to get a duty cycle of 66.66%, that and all we have seen in our previous sessions. Now, if I want to design a frequency division by 3 circuit with 50% duty cycle, this is my requirement. Okay, let me write down the requirement. My requirement is I want to design F by 3 with 50% duty cycle, with 50% duty cycle. Now, how to design this F by 3 with 50% duty cycle? Let us try to understand. If I want to design a frequency division by 3 with 50% duty cycle, then also I'm going to consider a mod 3 counter. Okay, let us consider a mod 3 up counter. I'm going to consider a mod 3 up counter. I'm going to consider a mod 3 up counter. Now, using this mod 3 up counter, I'm going to design a frequency division by 3 circuit with 50% duty cycle. Okay, let us see that. Now, before that, I'm going to consider few signals and few extra more circuits. Okay, so I'm going to consider two extra signals. One is enable 1 and another is enable 2. I am going to consider two signals. One is enable 1 and another is enable 2. Why I am going to consider this? I will explain afterwards. But let us try to understand. I need two enable signals, which is known as enable 1 and enable 2 signal. Okay. The requirement here is enable 1 signal will become 1, will be only high when count is equal to 0. And rest all cases your enable 1 signal will be equal to 0. Enable 1 will be high only when your count is equal to 0, and rest all cases your enable 1 signal will be equal to 0. Now coming to enable 2 will be only high when count is equal to 2. When count is equal to 2, whenever your count is equal to 2, then only enable 2 signal will be high, and in rest all cases our enable 2 signal will be equal to 0. This is our requirement. Okay, now what I'm going to do, I'm going to provide this enable 1 signal. So I'm going to take two flip-flops. These two are my T flip-flops. This is T flip-flop and this is T flip-flop, and this is a active high and this is negative edge or active low T flip-flop. So here I'm going to provide a clock with bubbled. Okay, clock with bubble. Okay, now here I am going to apply enable one signal, and here I am going to apply enable two signal. I'm going to apply enable one signal, and I'm going to apply enable two signal. Enable one signal is going to become one when our count is equal to 0, and enable two signal will become high when our count is equal to 2, and enable one signal is given to the input of our T flip flop, which is a positive edge triggered T flip flop, and enable 2 is given to a flip flop which is a negative edge triggered T flip flop. Now I'm going to get my outputs here. This, let's say this is my Q naught and this is my Q1. Okay. Let us first of all try to find out this Q naught and Q1. Let me draw the clock. These are my positive edges of clock. Now I am going to take a mod 3 counter. So mod 3 counter, it is going to start the counting from 0, 1, 2. Okay. And it is coming back to 0 again. 1 and 2. And again 0, 1 and 2. So this is my mod 3 counter. 0, 1, 2, 0, 1, 2, 0, 1, 2. Okay. Now this is my counter. Now my enable 1 signal should be high when my count is equal to 0. This is my enable 1 signal, and remaining all pulses it will be equal to 0, and again it will be high here, and again it is equal to 0, and again it is 1 here, and it is again 0. Okay, so this is my enable 1 signal, and coming to my enable 2 signal, it will be high whenever my count is equal to 2. Whenever my count is equal to 2. I think some of you have already got the answer why I'm going to take the enable 2 signal when my count is equal to 2. Okay, if not also I will explain. So this is my enable 2 signal. Okay, I'm going to apply this enable 1 signal to the positive edge triggered T flip flop, and I'm going to apply this enable 2 signal to the active or negative edge triggered T flip flop. Okay, so my Q naught now here at this positive edge of clock, if I can see my enable 1 signal, there is a transition. Okay, so what value should I take? Whether I should take 0 or whether I should take 1. So I am going to consider the value exactly before the positive edge of the clock. Okay, so here this is the value which I am going to consider. Let me take one more marker. So this is the value which I'm going to consider exactly before the positive edge of the clock, this value I'm going to consider, and this value will be sampled by the flip flop. And since the value is equal to 0, the input of the T flip flop is equal to 0, what is your output? It is constant. This is not going to change. Okay, this is not going to change. And at this positive edge of the clock, again there is a transition. So I'm going to consider the value exactly before the positive edge of the clock. So what is the value? This is my value. It is 1. Okay, this value is equal to 1. So if the input of your positive edge triggered T flip flop is equal to 1, definitely there will be output will be toggled. Okay, the output is getting toggled, and at this particular edge, the value before the positive edge of the clock is sampled, that is, it is equal to 0. So there is no change in output, and again here this value will be sampled, so your output will be toggle like this, and again here it is going to become 1, and here it is equal to 0. So enable 1 signal will become 1 here, so at this edge it will become 0. Okay, so this is my Q naught. Let me draw the Q1 also. Q1, how it is going to look like, let us draw. Coming to my Q1, Q1 is output of negative edge triggered T flip flop. Enable 2 signal is given as an input for our negative edge triggered T flip flop. So we are going to consider the enable 2 signal, and we are going to sample the values at the negative edge of the clock. So at this negative edge of the clock, we can see there is a stable value, that is 1. So if the input of your negative edge triggered T flip flop is equal to 1, your output is going to be toggled. So initially output will be equal to 0. At this instance, it will become 1. It will become 1. and where it is going to become 0 at this particular point, your value input is equal to 1, so output will become toggled here, that is it is equal to 0. And again at this instance it will become 1, at this instance it will become 1, and so on. So this is my output Q1, this is my output Q0. If you can observe here, if I perform XOR operation between this Q0 and Q1, if I perform XOR operation between this Q0 and Q1, let us see. So my output, which is going to look like this, XOR operation between this Q0 and Q1 up to here, it will be equal to 0. And from here, it is going to become 1. And at this edge, this will become 0. And again at this edge, it will become 1. And at this edge, it will become again 0, and at this edge it will become 1 and again 0. So if you can see my output, my time period of my output, if I can see, this is 1 clock cycle and this is zero point 0.5. This is 1 and this is 0 0.5. So 1.5 cycles it is on, and this is 0 0.5, and this is 1, and this is 1. So 1.5 cycles it is off. Again it is 1 cycle on and it is 0 0.5 cycles. So 1.5 cycles it is on and 0 0.5 and 1. So 1.5 cycles it is on, off. Okay, and this is 1 and this is 0 0.5. So 1.5 cycles it is on. So I can see here my clock if it completes 3 cycles. So here I can see carefully that my output is high for 1.5 cycles and it is low for another 1.5 cycles, and it is again high for 1.5 cycles and it is low for another 1.5 cycles. So here the duty cycle, if I can calculate duty cycle, which is equal to T on by T on plus T off, that is 1.5 by 1.5 plus 1.5, which is equal to 3.5. Convert it into percentage, it is nothing but 50% duty cycle. It is nothing but 50% duty cycle. And if you carefully observe here, here my Q0 value, it is equal to, here my Q0 value, it is high for exactly 3 cycles, and it is again, it is equal to low for 3 cycles if you can observe the Q0 value. So here we can observe that I cannot simply get the output exactly at any particular edge. Like I can get the output at either 1 cycle or either after 2 cycles or either after 3 cycles. Using the flip-flops, we can provide the output at the whole numbers. We cannot produce the output directly, like if we want to produce the output at after 1.5 cycle, or if we want to provide the output directly after 2.5 cycles using a single flip-flop, it is not at all possible. Okay, so that's why to have this 1.5 cycle, to have this extra half cycle width, I'm going to use this type of mechanism. So what I'm doing, I'm taking two signals Q0 and Q1, and if you can see this Q1, it is acting as it is getting activated at the negative edge. So if I perform the XOR operation, then I can get the frequency division by 1.5. Okay, so let me draw the circuit, how it is going to look like. So I'm going to take a mod 3 counter, and this mod 3 counter is going to have one output which is known as count, and whenever your count is equal to 0, enable 1 will be equal to 1, and whenever your count is equal to 2, enable 2 will be equal to 1. Okay, so this is my T flip-flops, positive edge triggered T flip-flop and negative edge triggered T flip-flop. So here I am going to apply enable 1 and here I am going to apply enable 2. Okay, and this is my clock which I have given here. This is my clock. This is Q and this is Q, and the outputs of this two are given to an XOR gate, and here we are going to get F by 3 with 50% duty cycle. F by 3 with 50% duty cycle. This is how we are going to design a frequency division by 3 with 50% duty cycle. Let us try to design frequency division by 5. Okay, so let us try to have, first of all, let us try to see frequency division by 5, and let us see how to design F by 5 with 50% duty cycle. Now, if I want to achieve frequency division by 5, then I should take a mod 5 counter. Then I should consider a mod 5 counter. Now for a mod 5 counter, if I can observe carefully, I will have three number of bits Q2, Q1 and Q0. That is 0. If I take a up counter, it is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. So this is 1, 2, 3, 4, 5. Okay. Now, if I only consider this Q2 output, if I only consider this Q2 output, let us plot this in a waveform. This is my clock 3, 4, 5, 6, and 7. These are my positive edges of clock, and I'm going to plot my Q2. Q2 is equal to 0 for 1 cycle, 2 cycles, 3 cycles. Q2 is equal to 0 for 3 cycles, and 4th cycle also it is equal to 0, and at the 5th cycle it is becoming 1. So this is 1 cycle, and again 0. Okay. If the clock is completing 5 cycles, then my output is completing only 1 cycle. So this is the time period of my output. This is my time period of my output, and this is my time period of the clock. This is T clock. So I can establish the relationship between my output and clock, that is T out is equal to 5 times T clock. And if I convert this into frequency, then F out is equal to 1 by 5 times of frequency of clock. So that's why if I consider a mod 5 up counter, and if I consider a mod 5 up counter, and if I only consider the output Q2, then I'm going to get frequency division by 5. And what is the duty cycle for this? Let us find out. Duty cycle is equal to T on by T on plus T off. That is T on by T on plus T off. Time period on by time period on plus time period off. So how many time period it is on? 1, and followed by 1 by 5. That is nothing but, if I calculate it in the percentage, then duty cycle, which is equal to 1 by 5, which is equal to 20 percentage. So if I consider a simple modify up counter, and if I take the MSB bit, then I'm going to get F by 5, frequency division by 5, with 20 percentage duty cycle. Let's consider case 2. Let's consider case 2, where we are considering mod 5 down counter. If we are considering mod 5 down counter. So what is the sequence of mod 5 down counter? It is starting from 1, 1, 1 and 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So this is my mod 5 down counter. Starting is 7, 6, 5, 4 and 3. Okay. Now if I consider this Q2, this is Q1 and Q0. If I consider this Q2, then let's see with the diagram. This is my clock. And if I'm going to consider my MSB, that is Q2, let us see how it is going to look like. So it is 1 for how many cycles? 1, 2, 3, 4 cycles. 1, 2, 3 and 4 cycles it is 1, and for 1 cycle it is equal to 0. So this is my time period. This is my time period. T out. Okay, and again it is becoming 1. Okay, and this is the time period of the clock. This is the time period of the clock. Okay, here if I carefully observe my, again, if output completes 1 cycle, then clock is completing 5 cycles. Okay, that is T out is equal to 5 times of T clock, and if I convert it into frequency, F out is equal to 1 by 5 times of frequency of the clock. 1 by 5 times of frequency of clock. If I consider up counter or down counter, and I can take a MSB, I'm going to get frequency division by 5 only. But the duty cycle changes. Coming to the duty cycle is nothing but how many cycles it is on? 1, 2, 3, 4. And how many cycles it is off? It is only 1. So 4 by 4 plus 1, that is 5. And if I can see, it is 80 percentage duty cycle. The duty cycle, it is nothing but it is 80 percentage. So this is how I can achieve a duty cycle of 80% if I am going to consider a mod 5 down counter. Now, if I want to get frequency division by 5 with 50% duty cycle. If I want to achieve f by 5 with 50% duty cycle. How to achieve frequency division by 5 with 50% duty cycle? The same method which I have followed for the frequency division by 3 with 50% duty cycle. Okay, how to achieve this? I'm going to consider a modify counter and I'm going to take two signals. One is enable one signal and enable two signal. Enable one signal will become one whenever your count is equal to 0. Now, when should enable two signal should become one? Actually speaking, it should become one at 2.5 cycles because f by 5, half of f5 is nothing but 2.5, right? But it is not possible because it cannot be high at exactly 2.5 seconds, right? So that's why we are going to make it high at whenever your count is equal to 3. Whenever your count is equal to 3, it is going to become high. Actually speaking, your count, it should become high whenever your count is equal to 2.5, but it cannot be happen. Okay, so that's why what we are going to do, we are going to make it high at third clock cycle. That is whenever your count is equal to 3. Okay, that is the reason. So I'm going to consider a mod 5 counter and I'm going to consider two signals. One is enable 1, which is going to become 1 when my count is equal to 0, and enable 2 is going to become 1 when my count is equal to 3. When my count is equal to 3, this is what I'm going to do. Okay, now let me, and what else I can do? This enable 1 signal is given to the positive edge trigger T flip flop, and this enable 2 signal is given to a negative edge trigger T flip flop. Output of the both T flip flops are given to a XOR gate, and the output of the XOR gate is nothing but f by 5 with 50% duty cycle. So enable 1 signal is given to a positive edge triggered T flip flop, and enable 2 is given to a negative edge triggered T flip flop, and both the outputs are XORed. Both the outputs are XORed. Okay. So let us draw the timing waveform for this. So these are my positive edges of clock, and this is my count. Let me draw the count. So for a modify counter, the count will be from 0 to 4. 1, 2, 3, and 4. 0, 1, 2, 3, and 4. Like this I'm going to have. So this is 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Okay, and coming to my enable 1 signal, it will become high and it will be 0, and again it is going to become 1 here. So it is going to become 1 here, and it is going to become 0. So this is my enable 1 signal. And coming to enable 2 signal is going to become 1 whenever my count is equal to 3, and it is going to become 0 here. And again whenever my count is equal to 3, it is going to become 1 here, and it is going to become 0. Okay, and this is given to the input of my T flip flop, and again the sampling, everything we should be careful. So let us say this is Q0. Q0 is nothing but output of the positive edge triggered T flip flop. Now my enable 1 signal is getting transition at the first positive edge of the clock. So I'm going to consider the value exactly before the positive edge of the clock, that is it is equal to 0. So the Q0 will be constant. Okay, at this particular edge, my enable 1 signal is equal to 1. The value exactly before the positive edge of the clock I am going to consider, and my Q0 will become 1 here. My Q0 will become 1 here. And again at this edge it is going to become 0, and so on. Okay, and coming to my Q2, it is the output of my negative edge triggered T flip flop. Okay, So where it is going to become 1 at this negative edge of the clock, if I can see the value of enable 2 signal is equal to 1. So at this edge up to here, up to this particular instance, it is equal to 0. Here it is going to become 1. And again at this instance, if I can see, this is my negative edge. At this instance, if I can see, my value of enable to signal is equal to 1. So it is going to become 0. And I'm simply going to perform the XOR operation between these two signals. That is, up to this instance, it will be equal to 0 and it is going to become 1. And up to this instance, it will be equal to 1 and it is going to become 0. And up to this instance, it is going to become 1 and it is going to become 0. Okay. Up to here, it will be 0. And here it is going to become 1 again, and again here it is going to become 0. So this is my waveform, this is my output. Let us try to find out the time period. So this is one cycle, you can see here this is one cycle, and this is second cycle, this is 1, this is 2, and this is 0.5. So 2.5 cycles, my output is equal to 1. For 2.5 cycles, my output is equal to 1. And for next, this is my 0.5. This is my 0.5. Okay. And for next, this negative edge to this negative edge. Sorry, this positive edge to this positive edge, it is 1. And from this positive edge to this positive edge, it is 2. So for next So for next 2.5 cycles, it is equal to 0. Okay. And again, for one cycle it is on, next one cycle also it is on, and next 0.5 it is on. So for 2.5 cycles, my output is equal to 1. And for next 2.5 cycles, it will be equal to 0. So here the duty cycle, it is nothing but it is equal to 50% duty cycle. This is how I'm going to achieve frequency division by 5 with 50% duty cycle. And if I want to achieve frequency division by 7 with 50% duty cycle, then what is half of 7? Half of 7 is 3.5. But I cannot get 3 point, but I cannot make my count exactly up to 3.5, right? So what I'm going to do, I'm going to take the enable to signal and I'm going to make it high whenever my count is equal to 4. Okay, so coming to conclusions, if I want to develop my frequency division by 3 with 50% duty cycle, let me write down here. If I want to have frequency division by 3 with 50% duty cycle, then my enable 1 signal will be 1 when count is equal to 0, and enable 2 signal will be 1 when my count is equal to 3. And what type of counter I am going to take? Mod 3 counter. You can take up or down counter you wish. Okay. And coming to F by 5 with 50% duty cycle, F by 5 with 50% duty cycle, I am going to consider a mod 5 counter. I am going to consider a mod 5 counter where enable 1 signal will be 1 when my count is equal to 0, when my count is equal to 0, and enable 2 signal will be 1 when my count is equal to 3, when my count is equal to 3. And if I want to consider F by 7 with 50% duty cycle, then I am going to consider a mod 7 counter. Then I am going to consider a mod 7 counter with enable 2 signal becoming 1 when my count is equal to 4, when my count is equal to 4, and my enable 1 signal will become 1 when my count is equal to 0. Here count is equal to 4 and here it is equal to 0. This is how I am going to achieve frequency division with 50% duty cycle. And in our next session, we are going to discuss about how to achieve frequency division with decimal numbers. We are going to have the same circuits with simple modifications. Okay. Yes. So that's all about this particular session. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this.